All right, recording is re-rolling. We are pretty near the end of class. You guys have been getting your data, doing a good job on this lab. Okay, so let's go over like the ideal textbook solutions. So for the first, so remember that your question, you're trying to figure out what's the coefficient of friction, coefficient of kinetic friction between two surfaces, so sliding past each other. And that's the ratio of friction force to normal force. So on the first half lab, it's pretty straightforward because, right, well, you see it right here. Second half, well, hang tight because we'll eventually get there. But let's see how this should have worked out. So this has some weight, maybe has a weight of example, call it 5 newtons, 5 newtons of weight. Okay. Now let's say you drag this across the surface at constant velocity. Maybe it takes like two, well, actually, what is that about? I'll say like 1.5 newtons to pull it, right? Your numbers might be different from mine. That's perfectly fine. Maybe you have different surfaces. Take the ratio, 1.5 Newton divided by 2 newtons. I'm looking at, sorry, 1.5 newtons divided by 5 newtons. Okay. Look at 0.30. Okay. And you could just do that all the way down. Okay. Then graph pulling force versus the weight. So that's this column versus this column. Do you guys see a bunch of XY coordinates? XY, 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 all the way down? So this could be F sub pull and some number of newtons, which you guys know is equivalent to the friction force. And this axis down here, the horizontal axis, could be the weight, also in some number of newtons. And you guys know that that's equivalent to the normal force. Okay. And then when you plot the points, and I've been walking around the class seeing you guys' graphs, and you guys looks like you guys have the right graph. Looks like this. There should be a direct relationship. Now, if you guys got data that does something a little different, then that's okay too. Your data is your data, but this is like an ideal textbook solution. Should be just a straight line like that, right? And then, oh, can you make an equation for that? That's what this box says, right? Can you make an equation? Does it look like y equals mx? Some version of that, y equals mx? Except instead of y, it's the pulling force or the friction force because they're equivalent to each other. Okay. Instead of x, it's either the weight or the normal force. Again, they're equivalent to each other. Okay. And hey, the slope. Do you guys catch the slope is the coefficient of kinetic friction? Okay. The slope right here, the rise over run, is the coefficient of kinetic friction. Okay. So the pulling force might be, I might say 0.30 times the weight. I might say 0.30 times the normal force, right? Or more generally, the coefficient of friction times the normal force, right? Isn't that true? That's equal to the friction force, right? There. Right. And then the second question, mu represents. So I think there's two good answers for this second box. You could have said the coefficient of kinetic friction, because that's what it is, right? I mean, that's a physics symbol for it. You also could have said the slope of the graph. The slope of the graph, F pull versus the weight. Could have done that. That's also true. It's equal to the slope of the graph. Okay. There you go. You guys good with the first half lab? You guys good there? Okay. All right. You guys ready to move on to the second half? Okay. Now the second half, remember this one was a bit more involved conceptually. All right. You were taking a surface, tilting it up at some angle and looking for this object to slide down at a constant velocity. Now, if it was sliding down at a constant velocity, then this would be a free body diagram that could represent that scenario where the normal force was the cosine component of the weight, but also the friction force was exactly balancing the sine component of the weight. Okay. Now, instead, I'm going to come back and explain a little bit more with that. So let's do that. Actually, let me hang tight on that. I'm going to do a little bit more proof derivation with that, but hang on to that idea. And so you guys had different weights. For example, maybe you had this 5 Newton weight again. So I'll put 5 newtons. Okay. And then maybe the angle that it broke at was let's say it was like 16 degrees, for example. I'm just gonna make something up, 16 degrees. Okay. Then I told you to take the tangent of that angle, and I didn't tell you why. But all you do is you pick up the calculator, you hit the tangent key, and then type in the angle, like 16 degrees, for example. I'm getting like 0.2867. I'll call it 0.29. 0.29. Right? The tangent of the angle. Right? You guys do that? Okay. Then I come down here, this graph, see it says tangent theta versus weight. Hey, that's like x, y coordinates all over again. So instead of y, it's the tangent of the angle, which is a unitless ratio, so there's no units there. Okay. And then the weight is still on this axis, and that could be measured in some number of newtons, right? Okay. Now, for this one, what you should have gotten, and walk around the class, so some of you guys got this, was pretty much the same tangent of the angle over and over again, regardless of the weight. So you could have big weights, small weights, but you're getting the same tangent theta over and over again. And actually, if that's true, the middle stuff that would have gotten you there is you should have had approximately the same sliding angle for, again, regardless of the weight. Big weights, small weights. It should have been about, actually, it should have been pretty close to what I got, somewhere about 15, 20 degrees. You guys get somewhere there about 15, 20 degrees all the way down, right? And then take the tangent, of course, you get the same thing, right? So this looks like a constant type graph where tan theta equals just some constant value. I'll say 0.29 because that's the data point that I have right here at 0.29. Okay. Is that okay? Okay, so far? All right, then big picture. Let's look at the second half compared to the first half of the lab. Huh. Do these two numbers look pretty close to each other? 0.29, 0.30. I wonder if there's a connection there. Remember at the beginning of class, I said that there should be some angle that's paired with some specific coefficient of kinetic friction. So if you change one, it's going to change the other, right? Let's chase down what that relationship is. I'm going to start with the circled expression. You guys remember the circled expression? Which from the first half lab was pretty straightforward. Just the coefficient of kinetic friction is just straight up the ratio of friction force to normal force. So we got that, right? But now let's do some substitutions based on this free body diagram. Because, hey, the friction force, isn't that equivalent magnitude to mg sine theta? The sine component of the weight? That goes right here. Mg sine theta. Right? Because that is that right there. Right? And, oh, how about the normal force? Normal force. Isn't that equivalent to mg cosine theta? It's right here. Mg cosine theta. You guys can do that, right? Oh, what cancels? The m and the g. So it shouldn't have mattered what lab mass you used. It should have broken at the same angle. And for that matter, you could take this around to different planets. That's what the lowercase g is, right? Different gravity fields, right? Who remembers this from math class? What is sine divided by cosine? Tangent. Tangent of the angle, right? And that is exactly what I had you guys do right there. Take the tangent of the angle. Okay, that answers this last question. How does tan theta relate to mu from the other, from the first half of the lab? The coefficient of kinetic friction is the tangent of the sliding angle. Bam. There you go. There's the whole thing. Once you got some data for each of your tables, you guys got graphs, and ideally they should look pretty well like mine, right? So the axes are scaled and labeled, and hopefully they take the same graph shapes as I have up here. Okay, you guys got these questions answered? Then pop your lab into the gray tray, and that is a wrap on today.